Welcome to week 6. This week we're going to be talking about complex numbers. So complex numbers are really important because, for one thing, they arise as solutions to differential equations very frequently. And this is because they're an important part of oscillations. They're a much easier way of modeling oscillations than using trig functions all the time. So let's look at an example of that. And of course, my favorite example is the spring. So we talked about this before, about how we can write the differential equation for a spring. So we all know Hooke's law, and we talked about how to write F equals ma as a differential equation. And I'm just going to rearrange this a little bit. And what we normally do is that we define this constant omega, and that makes how much you have to write a lot less. So to see how complex numbers are important to this, I want you to show how the following 3 solutions are solutions to this differential equation. So the first 2 are your standard sine and cosine. So these are all particular solutions to the differential equation. And I want you to show that that's the case. And remember, how you do that is that you do the left side and you do the right side, and you show that they're equal. So this third one is the exponential to the I omega t. And here, I is the imaginary number, which I hope you remember is the square root of -1. So you can just treat it as a constant. Okay, so pause the video, show that these are solutions, and we'll go from there. Alright, so I'm not going to work out the first 2 for you. I know you can do that on your own, and you can probably do the third one, no problem. But since we're talking about complex numbers today, I really want to drive this point home. So I'm working out the left side. I remember I squared is -1. That is what the imaginary number is. So that's the left-hand side. If we do the right-hand side, it's just minus omega squared times e to the I omega t. So these 2 are equal. So we show that it's a solution. So complex numbers are really useful for showing oscillations. And this is the most basic example of that, and we model lots of systems this way. And the reason this works out is because of Euler's formula, which we will come back to in a little bit, but I'll just show you real quickly what it is. So an exponential with an imaginary number in it is actually a combination of cosines and sines, and that's why it can model oscillations. We're going to use this all the time in mechanics. This is important also in quantum mechanics. But before we get on to all those interesting applications, let's review our basics. Alright, this is the second time I've written this down. So complex numbers have a real part and an imaginary part. And we normally represent complex numbers with the letter z. It's just a convention. So an example of a complex number is 4 plus 2i. So the 4 is the real part, and the 2 is the imaginary part. And one way we can write this is that we can write real part of z equals 4, and the imaginary part of z equals 2. So these particular abbreviations are pretty standard. So one thing that's cool about this part is that, and this is something we'll do in mechanics, is that when we write an equation with imaginary numbers, we can have a real equation and an imaginary equation. So let me show you what I mean. So here we have one equation and 2 unknowns, x and y. And normally that's not going to work out, but because this is a complex equation, it's really two equations and two unknowns because we have a real part of the equation. So the real part is 4x equals 8. So that's all the parts that don't have i's on them. And then you have an imaginary equation. So that's when you take the imaginary parts, everything that has an I in it, and write out that equation. So that's 2y equals minus 6. So see, we really have two equations for our two unknowns. So we can solve for x, and we can solve for y. Alright, I'm going to give you a couple to try yourself. Okay, so I've given you some complex equations. Each of them has two unknowns. I want you to solve for x and solve for y. Alright, pause the video and try it out. Okay, so let's write our real equation and our imaginary equation. Okay, pretty straightforward. Let's do the next one. This is pretty straightforward. The reason this is important, and one reason we're going to use it specifically, is in mechanics when you're solving the equation for a driven and damped harmonic oscillator. This is something you have to do in solving that equation. So driven means there's a force on your spring, and damped means there's friction in your spring. Okay, next thing we're going to talk about is plotting complex numbers. So we plot complex numbers in the complex plane. And please let me know in the problem solving discussion if you've done this before. So in the complex plane, what you have is that the x-axis is the real axis and the y-axis is the imaginary axis. So if we just talk about our example complex number 4 plus 2y, 1, 2, 3, 4 on our x-axis and 1, 2 on our y-axis, and we plot our point right here. Okay, that's pretty easy. So this is actually called the rectangular form of complex numbers. We're going to talk about the polar form. So in the polar form, we have the modulus, which is like the magnitude of the vector, and we have the phase, which is like the angle that represents the direction of a vector. This really is just like doing vectors, and I'm assuming that you're all quite familiar with vectors as you are all physics teachers. So the way that you write this is instead of writing x plus iy, you write the modulus times e to the I times the phase angle. And sometimes I'll just call this the magnitude, and sometimes, I just call this the angle, but it's the modulus and the phase. And remember, this is just like vectors. To write everything out a little bit formally, x is the real part of z, y is the imaginary part of z. The modulus r is the square root of x squared plus y squared. It's a right triangle. The phase, you just have to do a little trig to figure it out, same as with vectors. And so the real part, which is like the x component of a vector, is r times cosine theta, and the y part, the imaginary part, is r sine theta. And I'm going through this pretty quickly without showing where all this comes from in the triangles because I'm assuming you're very familiar with vectors. If that is not the case, please let me know in the problem solving discussion and I will come back and talk about it more next week. Okay, let's do an example. So let's take our complex number example we've been using. So I have it in rectangular form and I want to write it in polar form. So first we need to find out the modulus. which we can also write as the absolute value of c. So it's just the real part squared plus the imaginary part squared. That gives us the square root of 20. And if you want to leave your answer as a square root of 20, that's fine with me. But if you want to fix it up, you can do this as well. Alright, then we need to find the phase. Alright, the inverse tangent of 1/2 comes out to 0.46. And this is radians. I'm pretty much always going to use radians. If you want to look at degrees, this is actually 26 degrees. Alright, so if we write this in polar form, then we have the square root of 20 times e to the I times 0.46. Okay, let's do an example the other way. Let's say we're given the polar form and we want to write it in rectangular form. So the x component is r cosine theta. So that's 3 times the cosine of pi over 4. And the y component is the modulus times the sine of the phase. So that's 3 sine of pi over 4. So we're going to be using trig a lot, so make sure you know your unit circle or that you have a reference handy. And I don't particularly care if you have square roots in the bottom. I know some people do, but I'm fine if you just want to write it this way. So then our complex number in rectangular form looks like this. Alright, so I'm going to give you a couple to work out yourself. So what I'm going to do is I'm going to give you a complex number in either polar form or rectangular form. I want you to plot the complex number, and if I give you the number in rectangular form, I want you to write it in polar form. If I give it to you in polar form, I want you to write it in rectangular form. So I have 4 for you to write out. Okay, so these first two I gave you in rectangular form, so I want you to write them in polar form. The second two I gave you in polar form, so I want you to write them in rectangular form. Alright, pause the video, work them out, and then we'll go from there. Okay, let's start by plotting this one. So we're just going to sketch a plot. So this one is at 1 in the horizontal and square root of 3 in the vertical. Now let's find the magnitude. That's just 1 plus 3. So it gives us 2. Then we need to find the angle. I like to, well, a lot of times I like to use values that you can just get out of the unit circle. So this is pi over 3. So in complex, this complex number written in polar form is 2e to the I pi over 3. Alright, let's plot our next one. So this one is a negative real component and a positive imaginary component. And our magnitude is the square root of 1 plus 1. So our magnitude here is just the square root of 2. The inverse tangent of 1 is pi over 4. Now, I normally don't put signs when I'm taking inverse tangents. I normally just find out whatever value I would get if my angle is in the first quadrant, and then I think about which quadrant it's in from the picture. So this one's in the second quadrant, so I know that this angle should really be 3 pi over 4. So I'm counting on you being fairly familiar with trig so that I don't have to go over this in more detail during these videos, but I'm happy to talk about trig more in office hours or in the problem solving discussion if you're a little bit rusty. Okay, so this number is the square root of 2 times e to the I 3 pi over 4 in polar form. Let's look at our next one. So this one we're given the modulus and the phase. So a phase of minus pi over 4 puts it in the fourth quadrant. So this is the square root of 2 long, and this angle is pi over 4. Well, technically minus pi over 4. So we need to find the x component, which is the real part, and we need to find the y component, which is the imaginary part. And again, I'm just using values that you can get from the unit circle so that you don't have to use a calculator. So this is actually just 1, and this comes out to minus 1. So our complex number in rectangular form is 1 minus I. Okay, last one. So this one's in the first quadrant. Pi over 3 is about here. And this is 5 long. Okay, let's find our x component. So that's our real part is 5 times the cosine of pi over 3. And our imaginary component is 5 times the sine of pi over 3. We look at our unit circle and we find out this is 5 halves. And this is 5 times the square root of 3 over 2. So in rectangular form, this number is 5 halves times 1 plus I times the square root of 3. In this case, I've decided to factor out the 5 halves, and that's a matter of personal choice. Now, the important thing to be careful about, which is the same thing you have to be careful about when you're working with vectors, is pay attention to which quadrant you're in, especially when you're taking inverse tangent calculations. And as I said, I always do inverse tangent with purely positive numbers and then look at the picture to figure out what the angle actually is. Now, you may have different preferences in that. You may like to keep the signs, but it's really important to always reference back to the picture to make sure that the angle you're writing down is in the correct quadrant. Alright, let's go back to connecting to sine and cosine, which really is the most important part of using complex numbers when it comes to physics. So what we've been using is that the real component is given by r cosine theta, and the imaginary component is given by r sine theta. And this equals r e to the I theta. So we can rewrite this a little bit if we just cancel out the r's. Then we get e to the I theta equals cosine theta plus I sine theta. I gave you this at the beginning of the video. This is Euler's formula. It's really important. Now, it may seem like it kind of comes out of nowhere, but you can actually see how it works out if you expand each of these functions as series. So look at the series for e to the I theta, look at the series for cosine theta, add that to I times the series for sine theta. It'll all work out. And I encourage you to work that out for yourself if you're somebody who really wants to see where everything comes from. Personally, I don't like to show derivations until after somebody's been using something for a while, but let me know if you want me to show you that next week. And something else this means is that you can write sine and cosine in terms of exponentials. So I'll just show you what you get. And again, I encourage you to work it out for yourself that this is true. So you can write sine theta like this, and you can write cosine theta like this. I would emphasize that sine is an odd function, and this minus sign makes this an odd function. Cosine is an even function, this plus sign makes this an even function. If you want to prove this to yourself, then I encourage you to pause the video right now and work it out and show that this is true. Now what I want you to do is to use this in the case of an oscillation. So let's say we're writing an oscillation in the form a cosine omega t plus b sine omega t. This is the same omega we used at the beginning of the video. That's the square root of k over m. And a and b are just arbitrary constants. So this is one way you can write oscillations, as a sum of cosines and sines. What I want you to do is use what I gave you on the previous slide and write this in terms of exponentials instead. So use what I gave you on the previous slide, and then I encourage you to clean up any way you want. And you can even clean it up even more if you think about how a sum of arbitrary constants is still an arbitrary constant. So just keep that in the back of your mind. Alright, pause the video and try it out. Okay, so all we're going to do is plug in the expressions for sine and cosine in terms of exponentials. And here, theta equals omega t. So I've just written the over 2 out front. Okay, let's rearrange this a little bit. So I'm going to gather the e to the plus I omega t terms. Then I'm going to gather the e to the minus I omega t terms. Now here's what I was saying about arbitrary constants comes in. So a over 2 plus b over 2i, a and b are arbitrary constants. So I'm just going to rename this a prime. Same goes for here. This is a different arbitrary constant because it's a over 2 minus b over 2i, and I'm going to rename that b prime. Now this looks like a solution to differential equations that we are going to get all the time when we come back to differential equations later in the semester. So this is really important. Knowing that this is related to this is really important because you're going to get a solution to a differential equation with a complex exponential in it. And I want you to know that when you see a complex exponential, that is not exponential decay, that it's oscillations. Okay, hopefully that made sense. Let me know in the discussion. Okay, the last thing we need to talk about is the complex conjugate, which is pretty straightforward. So, in general, we have in rectangular form some complex number. Its complex conjugate, which we just write z star, is x minus iy. Easy peasy. Okay, if we are writing it with the modulus in phase, then the complex conjugate, you just change the sign on the phase. All this means is that if you're looking at it in the complex plane, that the complex conjugate is the mirror image of the original complex number across the real axis. So if we were looking at z equals 4 plus 2i, excuse my wobbly line there, we'd have some point up here. The complex conjugate is down here. If we were looking at a number in polar form, say 3e to the I pi over 2. Now this number is actually pure imaginary. Oh goodness, my lines are coming out wibbly. Alright, so that number is up here. Its complex conjugate is down here. Okay, that's all pretty straightforward. Why do we care about the complex conjugate? Well, one reason we care is it helps us get imaginary numbers out of denominators. So let's say we were given a number in the form, or you were doing some calculations with complex numbers, and you end up with this. Well, you can't tell what the real and imaginary parts are, or what the modulus and phase are in this form, because you have the I in the denominator. The way you get I out the denominator is by multiplying the complex conjugate on the top and the bottom. So this gets you 5 times 4, 20, minus 10i. Then on the bottom, alright, we get 4 times 4 is 16. we get plus 8i, we get minus 8i, and then we get minus 2i times plus 2i. Be careful with your signs, that just gets you plus 4. Okay, so what we have is 20 minus 10i. You see, what this does is that it makes the imaginary part cancel out, and you get 20 here. So we get 1 minus 1 half I. That's why it's useful. So I'm going to give you 2 just to try yourself, and what you're going to do is get that I out of the denominator. So pause the video and work that out. Okay, so our first one, we're going to multiply by 1 minus 2i on the top and the bottom. So on the top, that gets us 2 minus 4i. On the bottom, we get 1 minus 2i plus 2i, and then plus 4. So that equals 2 minus 4i divided by 5. Okay, now you can get to see what the real and imaginary parts are. And the second one. Here, we're multiplying by the complex conjugate of the number in the denominator. So it's 5 minus I. And we want to multiply this all out. So we get 20 minus 4i minus 5i. Alright, then we have minus I times minus I squared is minus 1. And minus times minus is plus. So this still comes out to minus 1. You gotta be really careful with your signs. This one on the bottom, we're going to get 25, and I know that the imaginary terms are going to cancel out, and I get plus 1. So I get 19 minus 9i divided by 26. Okay, so that's just a handy trick. Oh, and some other funny thing I wanted to show you. And it always surprises me to see this, is that when you take 1 over I and you multiply times I on the top and the bottom, what you end up with is minus I. So the other thing the complex conjugate is good for is finding the modulus. And yes, you already know other ways to find the modulus. And this is going to seem pretty redundant, but the reason I'm showing it to you this way is because it's really important in quantum mechanics. So if you want to find the modulus, another way of writing that is the number times its complex conjugate. When you take quantum, you are going to see the number times its complex conjugate all the time. And you're going to need to know that that's giving you the modulus. Okay, so I'll just show you an example, and you'll see that it just works out as you would expect it to. It's nothing terribly surprising. So you get 16, and you know that when you multiply a number times its complex conjugate that the imaginary parts cancel out. So we get plus 4. So you see all you're really getting is the real part squared plus the imaginary part squared. It's really not new information. It's just a different way of writing it that is useful when you're working with complex functions. So I'll just give you 2 to work out, and I want you to find the modulus of these 2 complex numbers using the complex conjugate, not using the other methods we learned earlier. Pause the video and press play again when you're ready to go. Alright, so this one we're just taking minus 3 minus 2i times minus 3 plus 2i. You know that the imaginary parts are going to cancel out, so this is just 9 plus 4, and you get the square root of 13. Okay, second one. Minus 1 times minus 1 is 1. Imaginary parts cancel out, plus 36. Just get the square root of 37. Again, I know this really doesn't look like new information, but when you're taking quantum mechanics, you're going to see functions all the time. The wave functions will be looking like psi star psi. That'll show up all the time. So that's all we need to do with complex numbers. Again, this is really important to what we're going to be doing with differential equations later in the semester and in classical mechanics. Next week, we're going to switch gears again and we're going to start talking about linear algebra and vectors, specifically how vectors work when we're using linear algebra. All right, see you next week.